In mathematics, you want to know what is true and why it's true. It's often hard to go straight from where you are to where you want to go. Each one of us has to find our own way. The boundary between knowing and not knowing is so clear in mathematics. You can almost see this mysterious region that our brain secretly operates. If you think about something long enough, you cross that line of understanding. When I was young, math was like a faraway land, surrounded by giant walls that I could not climb. I grew up in Korea and I dreamed of becoming a poet to express the inexpressible. I eventually learned that mathematics is a way of doing that. Now I am a professor of mathematics at Princeton University. I do research in combinatorics. My way was to build spaces from combinatorial objects. Once you have a space to move around, you can use your geometric intuition to extract information hidden in the original combinatorial structure. A good example of my work is the proof of the Dowling-Wilson conjecture. It's an old question, and the easiest special case of it is the following problem in plane geometry. Take a finite set of points on a plane and connect every pair of points by a line. Do we always get at least as many lines as points? Dowling and Wilson predicted that the answer is yes for points in an arbitrary dimension, comparing the number of planes of a given dimension with that of a complementary dimension, connected by a part of the initial point set. The conjecture can be formulated purely in the realm of discrete mathematics, but it's hard to prove within that same realm. So my collaborators and I imagined a space whose geometry untangles that difficulty. This imagined space has properties that are very similar to spaces that are familiar and more visible to us. And those properties allowed us to answer the original question using a totally different type of intuition. This is what happened in the case of Rhoda's conjecture and Dowling-Wilson's conjecture, and to a large extent, Mason's conjecture. I construct and analyze and wander in the geometric realm of my imagination. And when it becomes 3 o'clock, I go to pick up my kids from the elementary school. It really wakes me up. My wife Nayoung is the most important person in my life. She's my friend and companion and sometimes a teacher. She's always there for us. My older son Dan, we do a little bit of math together. Is it 30?
Yep.
Can I turn here?
No, you're not done yet.
He enjoys posing problems and watching other people solve them. It's like a puzzle and there's great joy in it. High five?
Okay.
My younger son, Saul, he just started walking. After dinner, we change into our pajamas and go to bed. And then we repeat the whole thing. There's beauty in this repetition. We are truly very lucky. Princeton is one of the best towns in the world to be a mathematician, and it's a peaceful place to raise our children. Every one of my works could not have been done without the help and influence of my collaborators. Being a part of a giant network of very good people gives me the freedom that I could not imagine before I became a mathematician. On clear days, I can see that I'm a small and simple part of a big and complex ancient structure. In some mysterious way, we are connected to each other, and we grow from that connection.